Okay, so today we're going to talk about scatter plots and correlation. So the first thing we need to talk about is bivariate data. Okay, in earlier chapters, all of the statistical summary measurements, like mean, variance, and proportions, they were concerned with describing univariate data. Okay, that's only measurements of one variable. All right, now to understand the relationship between two variables, data on both variables needs to be collected. This type of data is called bivariate data, which makes sense. Univariate versus bivariate. Uni means one, bi means two. So, two variables is bivariate data. So, the first thing we're going to talk about is looking for patterns in the data. Detecting a relationship between two variables often begins with a graph. In the case of bivariate data, a scatter plot is the traditional exploratory graphical method used to display the relationship between the two variables. So I have an example of a scatter plot given here. Now, with a scatter plot, we're comparing variable A and variable B. One is an independent and one is a dependent, typically, but it doesn't always have to be. When you have a scatter plot, you can have what's called the line of best fit. And you guys remember from Algebra 1 that line can, we kind of want it to be like as close to the middle of all of those points as possible. But something that's important to note here is that when you are dealing with scatter plots, outliers have a huge impact on where the line of best fit goes. An outlier can greatly affect that line of best fit. All right? Now, measuring the degree of linear relationship, the correlation coefficient. A scatter plot is a useful exploratory tool for detecting relationships between two variables. Eventually, however, a researcher will want to know the strength of the relationship between the two variables. Like, yes, I can give you a scatter plot. Yes, I can give you a line of best fit, but like I want to know the strength of that relationship. The correlation coefficient, which we recognize with a variable r, the correlation coefficient was developed to measure the degree of linear relationship. It is an index number used to summarize the strength of a linear relationship. So the computational formula for the correlation coefficient is given. Look at that. That's disgusting. Like, there is no other word for that formula for the correlation coefficient. That is disgusting. Horrid. I will accept that. Horrid. It is brutal. It is awful. But lucky for us, we live in 2022. And do you know what we have in 2022? We have Excel. And Excel will do that for us. Aren't we so excited for that? Yes, yes, thank you. So, before we talk about like how to find it, because I am not going to make you use this formula, I am not a monster. Before we talk about how to find it, let's talk about some properties of the correlation coefficient. Okay? Now, the correlation coefficient, again, we recognize it with the lowercase variable r, measures the degree of linear relationship, how well the data clusters around a line. Okay? That's what it measures. If the scatter plot indicates a relationship that is not linear, you cannot use r to measure the strength of the relationship. That's really important. The correlation coefficient only works with linear data. Okay, so if you like give me a scatter plot and it doesn't look like it has a linear relationship, it doesn't look like a line would work for it, correlation coefficient goes out the window. The value of r has to be in between -1 and +1. Okay, so it's like a little number line from -1 to +1. It is a unitless measurement. It has no units. A value of r near -1 or +1 means the data are tightly bundled around a line. A value of r near -1 or +1 means we have a very strong negative or positive relationship, such that predictions within the scope of the data are very reliable. Positive associations is indicated by r greater than 0 and has an upward slope. Negative associations is indicated by r less than 0 and a downward slope. And a value of r near 0 means there is no linear relationship between x and y. This is a lot of information, and like reading it really doesn't do as much good for us as like seeing it. So here's what we got. I have examples of correlation strength. All right. So I have 3 different scatter plots here. You guys can see on the first one I have a strong linear correlation. I have a strong linear correlation here. The relationship is very strong. It's very tight together. And like if I were to draw a line, all of the points are very close to that line. That is strong. Weak, you can see it's all still kind of going in the same general direction, but it's not necessarily close to that line that I did my best to draw. And then finally, none. If you look at this scatter plot, like the best line that you could probably draw is this dude right here. And can you tell me what would the slope of that line be? 0. That means the R value would be 0. And an R value of 0 means there is no linear relationship between x and y. So those are some examples. Now let's talk about what the R value means. The R value is best described on a number line. Okay, the R value is best described on a number line. Now remember, the R value has to stay in between -1 and 1. So this guy over here would be -1. This guy over here would be +1. Okay, this guy over here would be +1. In the middle, we would have 0. Okay? Now, if you have an R value of +1, that is going to be a perfect positive correlation. If you have an R value of +1, that is a perfect positive correlation. That is very rare. I don't think I've ever seen an R value of +1. Okay? The same thing happens with negative. If you have a -1, that is a perfect negative correlation. Okay? Perfect negative correlation. Now, in the middle of that, if you have a 0, an R value of 0, we already said that means there is no relation. No relation. An R value of 0 means there is no relation. Now, what if we talk about things in between that? So, for example, we could also have an R value of +0.5. Okay? Similarly, we could have an R value of -0.5. Now, if your R value is in between 0 and +5, that means you have a weak positive correlation. You have a weak positive correlation. If you have an R value between -0.5 and 0, that would be a weak negative correlation. A weak negative correlation. Okay? Now, if we were to keep going in between that, so for example, if I were to focus on 0.8, if you were to have a correlation value between +0.8 and +0.5, that would be a moderate. That would be a moderate positive correlation. Same thing with in between -0.5 and -0.8. That would be a moderate negative correlation. And then finally, in between a +0.8 and +1, that would be a strong positive. And between negative and negative, that would be a strong negative. Now, the reason we have this number line is so you understand when you get an R value back, when you get that correlation coefficient back, and you see a number, you can kind of start imagining what the scatter plot is going to look like in your mind. Now, these numbers are not set in stone. Let's say you get back a correlation of 0.55. Like, if you're like, I don't know if that really means if it's a weak positive or a moderate positive, listen, it's not like live or die by this, okay? It's really kind of more like, well, it's in the area of weak to moderate. Does that make sense? Like, these are not set in stone. But it's to help you understand, if you get a correlation coefficient of 0.87, you have a strong positive correlation. Okay, your data is fit pretty tightly around that line of best fit. Okay, there's not very much variance there. Now, some examples of this are right down below here. If you have a perfect positive correlation, like look down here, this perfect positive correlation means it has a correlation coefficient of 1. If I were to draw a line, to the best of my abilities, because I suck at drawing lines today, if I were to draw a line of best fit, every single one of those points is on that line. That is what a perfect positive correlation and a perfect negative correlation. That is what a perfect correlation means. Every single one of those points on your scatter plot fits on your line of best fit. Okay? Then a high positive correlation, that means they're all pretty close to it. They're all pretty close to it. Low correlation, they're all getting further away. No correlation means I could draw a line anywhere that doesn't help me. Okay? Now, something that I hope that you're taking note of and that you notice here is that when I have a positive correlation, what kind of slope do I have? It's also positive. If I have a negative correlation, what kind of slope do I have? Negative. So the slope and the correlation kind of go hand in hand. If you have a positive slope, you're going to have a positive correlation. If you have a negative slope, you're going to have a negative correlation. Again, that's why when we have a correlation of 0, that horizontal line that I drew has a slope of 0. There is no correlation there. All right? So that being said, let's go down to examples because none of this is new to you. So let's go down to these examples and let's try and figure some of this stuff out. Number 1 says, the following data gives the number of hours 5 students spent studying and their corresponding grades on their midterms. Calculate the correlation coefficient and round your answer to 3 decimal places. Now, to calculate the correlation coefficient, you would have to use that really long, nasty, horrid, abhorrent, terrible formula. We're not using that. I'm not a monster. I'm not going to make you do that. Instead, we're going to use Excel. And Excel has a correlation coefficient formula. Now remember, if you are on a test and you're like, I don't remember how to find correlation, your best bet is to literally start typing the word. If you have to find the correlation coefficient, you're going to type in equals. And then if you start typing in that word, C-O-R-R-E-L, correlation, look, C-O-R-R-E-L returns the correlation coefficient between 2 data sets. Boom, amazing, done, right? Now, before we do that, we need to get this table looking a little nicer, okay? It's not a great table, so let's highlight it and copy it. Oh, I want the whole table, thank you. Copy it. And then I'm going to paste it down here, and what do I need to do to it? Transpose it, good. So home, paste, special, transpose. Now, I hate it when I can't see what they're saying, so I always wrap that text so I can see it a little better. Now, once you do that again, we're going to find the correlation coefficient. So all you have to do is you have to type in equals, C-O-R-R-E-L, open parenthesis, and notice it says array 1 and array 2. It does not specify which one has to go in first, which one has to go in second. We have 2 columns in my table here. One of them is array 1, one of them is array 2. Do not include the titles. We're only working with the numbers here, okay? It does not matter which is first. So if I wanted to, I could highlight the hours spent studying first, comma, the midterm grade second, close my parentheses, and hit enter. And guys, if I did it the other way around, I'll just show you here. If I would have done this guy first, comma, this guy second, guess what? I get the same thing. Okay, it does not matter which one you put first and which one you put second. Okay. Now, that is my R value, but they want it rounded to 3 decimal places, so let's make sure we do that accordingly. And let's talk about what that means. If I have an R value of 0.967, what does that mean? It is a strong positive correlation. So if I were to take these points right here and I were to put them on a scatter plot, it would have a strong positive correlation looking something like that. That would be a strong positive correlation. Okay? They would all be pretty tightly knit around that line of best fit. Okay? Another way, another example I like to talk about the line of best fit, okay, in a scatter plot, is if like right now someone were to get on the announcements and be like, attention, we have an assembly down in the gym. All at once, everybody would start moving in the same general direction, right? We would all start moving towards the gym. Now, would everybody be walking in a single file line? No, absolutely not. But we're all moving in the same general direction, which would mean we're all kind of like a scatter plot with a strong positive correlation. Does that make sense? That's how I relate correlation coefficient. So let's talk about avoiding some correlation pitfalls. A high correlation does not imply causation. This is very, very important. A high correlation does not imply causation. Sometimes that happens, but it does not imply it every single time. Here's what that means. Suppose that a high correlation has been observed between the weekly sales of ice cream and the number of snake bites each week. It seems unlikely that ice cream sales would cause snake bites, or would cause to bite, goodness, I cannot read, would cause snakes to bite people, or that more snake bites would cause ice cream sales. Okay, so the correlation between those, they're trying to figure that out. Yet, when the data are analyzed, you may find an unexpectedly high correlation. If the two variables aren't actually related, what could explain such an observed relationship? Tell me, do you think ice cream sales, high ice cream sales, would cause a high number of snake bites? Do you think one causes the other? Absolutely not. I don't think snakes typically love ice cream sundaes. I am assuming that. I don't think they're going to come after that. I don't think that's the cause of that. Instead, the apparent relationship is an illusion caused by a phenomenon called common response. That means that both variables are related to a third variable. Tell me, what third variable do you think high ice cream sales and snake bites are related to? Heat, high temperature, yeah? In this case, the high temperatures in the summer cause increases in both ice cream sales and reptile activity. The high summer temps would be confounding the relationship between ice cream sales and snake bites. That word confounding is a new word. Sometimes this confounding effect is referred to as a lurking variable. A lurking variable. Observational studies are particularly vulnerable to confounding variables. A good design of experiment can minimize the effect of confounding. Some statisticians differentiate between a confounding variable and a lurking variable by whether the researcher is aware of the confounding variable. Okay? Lurking variables are confounding variables that the researcher is not aware of. So here, with our example of the snake in the ice cream cone, the high temperature is a confounding variable because we're aware of it. We know, okay? But a lurking variable is a confounding variable that we are not yet aware of. Like we're saying, okay, these two are really related, so maybe there's some causation there, but instead there's actually a confounding variable that we don't know about yet. That is what a lurking variable is. Correlating summary measures, such as means, will tend to provide an inflated correlation measurement. Ignoring the variation of the individual values magnifies the correlation measure and gives a somewhat distorted view of the underlying relationship. Okay? So when you are creating some kind of experiment, your goal is to eliminate confounding information. Your goal is to eliminate confounding information. You want to minimize that as much as possible. Yeah, hold on. Play. Thank you. All right. Suppose there's a good reason to believe that a causal relationship exists between two variables. But when a correlation is performed, the value of the correlation is near zero, indicating that there's no association. Does the lack of correlation between the two variables prove that no relationship exists? And the answer to that is no. There are several reasons two related variables might not have a high correlation. So, for example, we specified earlier that a correlation coefficient only works with linear relationships. Well, you guys have been through algebra and algebra 2 and some of you FST. We are all aware that linear relationships are not the only kind of relationships that exist. Like if you look here, what kind of relationship is this? It's exponential, and R value is not going to work on an exponential. Same with U-shaped or quadratic. Like you will notice that that is a relationship. Some values can be related that way, but you're not going to have a correlation coefficient to go along with it. An example of that would be like COVID cases. Like if you notice COVID cases like started down here, and then they like peaked, and then they went back down, that's a relationship. And what caused that peak was like the cold and flu seasons, right? But there is no correlation coefficient relating those two. Does that make sense? All right. So the next thing we're going to talk about is fitting a linear model. Okay, even though the correlation coefficient is used to measure the degree of the linear relationship, how strong it is, it does not describe the exact linear association between x and y. That is the role of regression analysis. By determining a specific relationship between x and y, we may be able to use x to help predict y. Otherwise known as, we want to write the equation for the line of best fit. We all know the equation for a line is y equals mx plus b, where m represents the what? Slope, and b represents the y-intercept. Well, like everything in math, this textbook does not like to make it easy, okay? It is still the same equation that we're using, but they changed it. Statisticians like to use this stupid equation. Look at that equation. Do you see how it is the same? Yes? Do we still have our slope? And do we still have our y-intercept? Yes. They changed the variables. Now my y-intercept is b sub 0 and my slope is b sub 1, and they also flipped the order. Is it absolutely ridiculous and asinine? Absolutely, I believe so. But I also believe in your intellectual capabilities. I believe that you guys are smart enough to understand this, okay? So once we create the equation of a line, how do we measure how close that line is to our data? Like, that's really important. I can give you a whole bunch of points and say, boom, create me a line of best fit. And we did this in Algebra 1, where you took your ruler and you drew a line to the best of your abilities that split those points in half. You wanted half on top and half on bottom. Well, that means that sometimes Jordan's line was different than Aisha's line, okay? Things are going to be different because of human error. So how do we determine which line was best? Was Jordan's line more accurate or was Aisha's? How do we know? Okay? Well, to do that, we have to look at what's called the error. The error. Meaning, like, if I look at this line right here, this point has more error than this point over here, right? Because it's further away. There is more distance between that point in the line than this line over here. Same thing here. If I were to take this point right here, there is more distance between that point in the line than there is this one. Okay, so you would have to come up with the error, find the distance from each point to the line, and then average them, right? Now again, here's the problem. All of these points up here would have a positive error, right? And all of these points down here would have what kind of error? Negative error. Well, the problem with that is when you take all those positives and add them to all those negatives, you're going to come back with nothing, right? You're going to get 0. Well, that's an issue when we're trying to figure out the error and figure out, well, how close and how far are these guys really? That's where a new formula comes into play. And that formula is called sum of squared errors. So you guys have kind of done this before. When you have a bunch of positives and a bunch of negatives and you want to find out like their average distance, to eliminate that possibility of having all of these positives cancel out all of these negatives, instead you take those numbers and you square them. Because when you square them, it creates all positive responses, right? So when you have the sum of the squared errors, it's going to give you a better observation of it. Let me show you an example because it's a lot easier to understand when you can see it. Just a minute. Got a nice little gizmo here for you. All right, check it out. Here we have a scatter plot, and I want to come up with the line of best fit. Well, if I want to fit a line, here I have one. Is that a good fit? Why not? We actually probably wanted to have what kind of slope? A negative slope. So if I move my little guy over here, is that closer? Is that a better fit? It is a better fit than what we started with, but now what do I need to do? We need to move the y-intercept. We need to shift it down. So we're trying to find a good relation for this line. But who's to say that this line right here is a better fit than this line right here? Like, how do we know? And that's where the error comes into play. Now check this out. When we square the errors, here's what it looks like. Okay? So the distance from each point to each line is going to be the error squared. So right now this line has a total error of 27.4. Now I can manipulate that and move that around. Let's see if we can make that error less. If I move it up, that error is getting bigger. That's not working. If I move it back down, ooh, look, I got 26.86. I got 26.44. Then, ooh, 25.96. Let's see if we can make it even smaller. 25.9. Looks like 25.9 is the smallest that I can get. Do you guys agree? Now, if I actually find the correct least squares fit line, ooh, they went way, way better. So their slope was a little bit different, and they got an error of 21.61. So I was close, but I could have gotten a lot closer. Does that make sense? So that's why we don't want to rely on our human brains and our human eyes to be like, oh, that's pretty close, because we can still get it closer. Okay? So by using this method, this squares, the sum of the squares to find the error, we can find as close as possible. Well, that being said, let's look at this example. It says, consider the following data regarding students' college GPAs and high school GPAs. Goodness. The estimated regression equation is the estimated college GPA equals 2.29 plus 0.1234 times the high school GPA. Okay? Now, notice, here's what they're doing. They're saying this is my x value and this is my y value. If I substitute a high school GPA in for x, I can multiply it by the slope, add it to the y-intercept, and I get my estimated college GPA. Compute the sum of the squared errors for the model. I'm going to change that. For the model. Round your answer to 4 decimal places. Well, this is the formula that we're using. Okay, this is the formula that we're using. This formula looks really intense, but again, all you have to do is break it down. The sum of the squared errors is literally exactly what it sounds like. The sum of the error squared. Now, we just have to figure out, what does that word error mean? Well, the error here is the difference between the y values minus the y hat values. Now, here's what y and y hat mean, okay? Y is the observed, and the y hat is predicted. There's a difference between observed and predicted. What I observe is actually really happening. What I'm predicting is what I think is going to happen, okay? Now, they even split that up a little more. They're saying y minus, like the actual value, minus what I predicted. So let's figure this out. To compute the sum of the squared errors, here's what we got to do. The first thing we need to do, we have an observed right here. Do you guys see that? That's what they actually observed. Okay? They're saying, we think the higher GPA you have in high school, the better you're going to do in college. And we have this data. Here's all these high school GPAs. Here's all these college GPAs. Now let's use this formula that they told me about to figure out what the predicted or the estimated college GPA was actually going to be. And they tell you how to do that with this formula. To find the estimated college GPA, you need to take 2.29 plus 0.1234 times your high school GPA. So you're going to come in here, and you're going to hit equals 2.29 plus 0.1234 times your high school GPA. So I'm going to click on that high school GPA. Then we're going to drag it on down. Okay? That is your predicted. Okay, that is your predicted. That is what we said. Okay, here is my formula based on that formula, if you have a high school GPA of 4.9, I am predicting that you're going to have a college GPA of 2.89, okay? Now, according to this model, we need to take the observed and subtract the predicted. This is my y values, and this is my y hat values. So we need to take the observed minus the predicted. So that's going to be my next one. Observed minus predicted. So I'm going to hit equals, and I want my college GPA minus my estimated college GPA. Then we're going to drag it on down. Okay? Then, according to this formula, I have the observed minus the predicted. Now I want to square it. So the next one is just going to be squared. Okay, so just so we're all on the same page, this observed minus the predicted is actually my error. That is the error. Because the observed and predicted, the difference between what I observed and what I thought it was going to be, that's where I have some error going on. That's my error. So the next column is literally going to be my error squared. So I'm going to hit equals, and I want this cell squared. And the reason we square it is to eliminate those negative symbols. We're going to drag that on down. And then finally, you have to think about what they're asking you. They're asking you to find the sum of the squared error. Well, here I have a column of all of my squared errors, so all I have to do now is find the sum of it. So I want the sum of all of these squared errors. And that value is going to be my SSE, and they want it rounded to 4 decimal places. Oh, not SS, SSE. Now, what I've done below that is I've given you just like a little information of how to compute that. So if you're like, I don't remember how to do that, I don't remember those steps, it's right there, steps 1, 2, 3, and 4. Find the predicted, find the error, square it, sum it up, okay? So that has a squared error, the sum of the squared error of 2.754, which is crazy considering that little gizmo we did, their error was like 21 point something. So like the sum of the squared errors is kind of hard to understand. But our goal is to get that number as low as possible. Okay, to get that number as low as possible. So my question would be, how on earth do we find the line with the least amount of possible error? With Excel. Excel is going to do it for us. Excel has the capabilities to calculate, to compute the perfect number so we have the smallest amount of error. So number 2, it says, a pharmacist is interested in studying the relationship between the amount of a particular drug in the bloodstream and the reaction time of the subjects taking the drug. That's a pretty important relationship. Like, we need to know, if you take this drug, is your reaction time going to be delayed? 10 subjects were randomly selected and administered various doses of the drug. The reaction times in seconds are measured in 15 minutes after the drug is administered, with the results given below. So the amount of drug given in milligrams right here, and here's the given reaction times, okay? Now, this is really important. Like, if you take a medication and they're saying, like, hey, do not operate heavy machinery after taking this medication, when they say that, they're literally talking about cars. They're not saying, like, don't go run a bulldozer. They actually do mean that as well. But more importantly, they're saying, don't go drive your car. That is a piece of heavy machinery, heavy equipment, because your reaction time is slower. That means they've done these experiments. So we want to write the line of best fit for this data with the least amount of possible squared error. Okay? So here's what we're going to do. First thing we need to find is the slope of this line. Okay? The first thing we need to find is the slope of this line. And guess what? Excel can do that. Now, if this was in algebra, you would have plotted all of those points, and again, you would have moved your straight edge all the way over until you're like, oh, there's about half of the points above and half the points below. I'm going to use these 2 points, find the slope, write the equation. No. Excel is going to do it for us. And here's how we're going to do it. We're going to type in equals, and what are we finding? So what do you think we're going to type in? Yeah, we're going to type in slope of, but this is very important. When we found the correlation coefficient, it didn't matter which one went first. We could do the x's and the y's or the y's and the x's. It didn't matter. When it comes to slope, it does matter. Pay attention to what they tell you. They want your known y values first. So the y values is the dependent or independent value? Dependent. Which one is dependent? Which one can we, the reaction time, very good. So this is my y values here. Comma, the known x's are my independent values. The amount of the drug. And when you do that, boom, that is the slope for those points. What else do we need to write an equation? The y-intercept, right? The y-intercept. What are we finding again? Intercept. So what do you think we're going to type in? Intercept. Look at that. And again, it is very important that you pay attention to what they want. They want the y values first. Oops. I want that to go down to D43. And the x values to come second. Okay? And there you have it. Now, with that information, I can write an equation. I can say y equals, now I'm going to do it like I normally do because I also teach algebra. I'm going to put the slope first, 2.24 times x plus my y-intercept, 7.68. Now, is that perfect? No, because I rounded it. But if you use the Excel functions, it is perfect. It is perfect. And I'm going to prove it to you. Let's find the correlation of it. So let's find the R value. So equals correlation of, and remember, with the correlation, it does not matter which ones you choose first, x's or y's. Some people like to do the y's first because you have to do the y's first with the slope and the y-intercept. That's fine. What kind of correlation do you get? Oh, super strong positive. Is it perfect? Why is it not a perfect one? That's not true. Have you met me? I am super perfect. So here's the thing. This cannot be a 1 value because these points don't make a perfectly straight line. No matter what we do, these points, like look, this goes up by 2 and then it goes up by 3 and then it goes up by 2 and then it goes up by 1. There is no possible way that it could be a perfect straight line because the reaction times do vary. So what I'm saying is this is as perfect as we can get with this data set. Okay? Now that being said, let's look at number 3. Suppose a company wishes to predict sales volume based on the amount of advertising expenditures. The sales manager thinks that sales volume and advertising expenditures are modeled according to the following linear equation. Both sales volume and advertising expenditures are in thousands of dollars. That's really important. Pay attention to things like that. Oh, that's not what I wanted. Pay attention to things like that when you're on Hawks, when they say are in thousands of dollars, because in this formula it says the equation is estimated sales volume equals 47.81 plus 0.47 times the advertising expenditures. This is in thousands of dollars. So instead of making this formula $47,810, they shifted it to decimals. If the company has a target sales volume of $175,000. How much should the sales manager allocate for advertising in the budget? Round your answer to the nearest dollar. What do I do? Ouch. My Algebra 1 kids could do this. Did they give us the formula? Absolutely they did. And then they give me a target sales volume of $175,000. Where would I put that? Would I put it in for estimated sales volume or for advertising expenditures? I would put it in for the sales volume because it has a target sales volume of $175,000. What number am I putting in there? Do I put in $175,000? No, because it says both sales volume and advertising expenditures are in thousands of dollars. So we would put 175 in. Because if that was in thousands of dollars, it'd be 175,000. So 175 equals 47.81 plus 0.47 times my advertising expenditures. Now what do I do? How do I solve? Subtract 47.81, so equals 175 minus 47.81. And then we're going to divide it by 0.47. But we need to answer the question. The question says, round your answer to the nearest dollar. How much should the sales manager allocate for advertising in the budget? Should he allocate $270? Good. This is in thousands. So what we're going to do is I'm going to come over here, and you can either like round it yourself, like move the decimal, or you could just multiply it by 1,000. Either is okay with me. And this is in dollars. And we want nearest dollar, so I'm going to move that bad boy over. So he should allocate approximately $270,617.